All right. So, yeah, all of the notes and the videos are posted. So, if you want to review them or look at them, they should be available. Um, and yeah, your Problems at 5 is in your hands. There are office hours today. Um, as I think I mentioned, I will be traveling the last week of April. And so we won't be having lectures then, because there's really actually a number of seminars and there's no way during my time to do Zooms. So I'd like to think about some potential time for makeups. Generally Mondays are good for me. We can think about Mondays bad for people. But I can email you. We can try to find. Hopefully, there's a non-null set that we can find that will be good, or at least possible for everybody. All right. There's also the possibility of what I used to call bonus lectures during finals week. You know, we do have a final, so there's time for extra lectures, so we could do lectures during the final. I know, crazy man. So
that's what being in grad school is about.
We can think of that. All right, so we've been talking about, you know, the idea of a quantum map, and particularly a completely positive map, which has the more general description of a map for an open quantum system. And we've said that we can describe this map in many ways, including through a so-called measurement model, where we think about the input-output map as I have some quantum system and the quantum environment, and there's some unitary evolution between them, and if we say there's some state of the system, and then there's some that's uncorrelated, very importantly, from the environment, which we can take to be a pure state without loss of generality, then the input-output map tells me that the output state of the system, some map on the input, which we can think about to trace over the environment of the system environment coupling, which we can always write as a Krauss map. Where the Krauss operators, or the measurement operators, are equal to the partial matrix element of the generally entangling unitary between the system environment, starting from the fiducial state and then ending in the state mu, which we can think about as some basis of states for the environment. And as we said, that we can think about this in terms of a measurement model. We'll come back to that. That measurement model is both important conceptually in thinking about how information is gained and lost, and how we should think about open quantum system dynamics, but it's also important from a calculational perspective, and something we'll talk about in a few weeks, and will be the topic of your final project, the so-called quantum trajectories, or the quantum Monte Carlo wave function method, but that's for another time. Okay, so this is an input-output map, and what we want to now talk about a little bit more, get under the hood about this, is to talk about dynamics. So this is just kind of a general input-output map, but it's not a description that we usually think about in physics, where there's something evolving as a function of time, right? And so, we might want to think about the state of the system as a function of time. And we want an equation of motion. Usually we think about that equation of motion as a differential equation in time, okay? Now, we know from closed quantum system dynamics, the Schrodinger equation tells us how to evolve the quantum state as a function of time. And so let's just review a little bit and just think a little bit about what are some of the properties that we know about when we think about closed quantum system dynamics. Where we have unitary evolution. And there are certain properties that we know about the unitary time evolution operator. So I can have an operator, unitary operator, that, say, evolves the state from a time t to a time t plus tau. That's my time evolution operator. And that time evolution operator would, take the state at a time t and evolve it to some later time. In particular, if it's a differential time, then that is a way we can get the differential equation that tells us how to evolve the state's function. But let's think about some of the properties of that time evolution. So in particular, what we know is that if let me just think about something about my notation here, yeah. So there's a composition law that I have for time evolution. So if I take the state, if I have a time evolution that takes me from time t to t1, and then from t1 to t2, where let's say t1 is between t and t2, then what I get is the time evolution that takes me from, right? So I can compose this. I go from t to t1, and then from t1 to t2. And in particular, if I have the situation, if the Hamiltonian, which we'll talk about in a moment, the generator of time evolution, is time independent. So there's no explicit time dependence. So there's the way in which a system evolves in time is not changing with time. The system is time translationally invariant. Then the other thing we know is that this only depends on the time difference, right? It doesn't depend on where I am in time. It just depends on the time difference. And I can think about this. Typically, we would write this as just, the time evolution operator over that time interval. It's stationary, right? That's if I have a time independent Hamiltonian. These are some general properties, and then from that follows the Schrodinger equation. Okay, and let's just write it in particular for this case, because what we have then is that if I look at, so let's just take H time independent. Just for simplicity, we don't have to do that, but it's just a little easier to deal with. So first I evolve the system from 0 to some time t, and then I evolve it for another dt later, and that gives me the time evolution from 0 to t plus dt, right? What's important about this operator is that this thing should be, if this is a dt, this is only first order in dt, and should go to the identity. So if I say that the doing nothing is the identity, so this should go to the identity when dt goes to 0. And so that tells us the form of the unitary. It must be of the form, the identity, plus something proportional to dt. And if it's going to be unitary, and that means that u dagger u should be 1, then I gotta have something over here that is gonna cancel, and that's gonna be proportional to I. And by convention, we say it's minus I over h bar for reasons that we can discuss. So this is my time evolution for a small dt, okay? And from that, it follows that we get the Schrödinger equation. Or equivalently, du dt is minus I over h bar h u. So that's an expression that tells me how to evolve the time evolution operator. Of course, the solution to this is that, again, for a time-independent Hamiltonian. Moreover, I can say that a state of system, there's some map for unitary operators, unitary time evolution, which is that. And from that it follows that this is an expression of the Schrödinger equation for the state of the system. Okay, this would be true even if the Hamiltonian were time dependent, but this makes it a little more straightforward to not deal with that, right? And that just, so the fact that we have this generator, which is the Hamiltonian, gives us this expression for the time evolution, and this is the Schrödinger equation, also known as the von Neumann equation, which is just a form of the Schrödinger equation when the initial state need not be a pure state. This is just a generalization. But the evolution is unitary according to the Hamiltonian. And we can solve, and we solve for the dynamics of such problems, okay? So that's the problem for closed quantum system, and we know how to evolve dynamically. We have an expression for the whole map evolves according to a differential equation, okay? But what about for an open quantum system? So in an open quantum system, life is a little more complicated. If I have an open quantum system, you know, we can say, okay, I want to evolve over some amount of time. We can do that, formally speaking, just as we discussed up above. There's some time evolution of the joint system. There's some fiducial state of the ancilla, or the environment, and that gives us the map. But can I think about this? Is there an equation of motion for this map that's equivalent to the Schrodinger equation for the unitary? Some way in which we would say there's some generator of the map like the Hamiltonian. It's not the Hamiltonian because it's not unitary, but maybe it's like the Hamiltonian. What would it take? How would we look at that? Well, the first question is this even true for the open quantum system? So this, of course, I can think about if there's some Krauss map. That's fine. That's the general form we had before. This, we can always write that down. That's formally kosher. I'm only formally kosher, I'm not practically kosher. But what about if I wanted to look at this from t plus tau, right? So that's the state. Does this equal, I just evolved, let's assume we have a time translation invariant problem, just be like before. The Hamiltonian and the nature of dissipation is not fluctuating or in any way the question is, does this equal that? That is to say, if I want to get what the state is, this is the state at a time t plus tau, by definition. By definition, I take the state at time t equals 0, I evolve for this amount of time according to that map, and this is the state at that time. Can I obtain that by first evolving the state for a time t, and then evolving it for a time tau? Can I just compose these guys in the same way that I composed the unitaries? And the answer is no. Why not? I mean, the answer is generally no. You can kind of see that just by, you know, looking at what this guy is, right? So, I screwed it up. This is the wrong board. Will I ever learn? Right, this is equal to that. It's the Krauss map associated with evolving for this amount of time. But the composition of the two is, okay, I evolve for that extra time tau on that state. But this is the sum over mu prime and mu prime t rho 0 and mu prime t. And if I multiply all that out, I'm not going to get this. I mean, the math shows, but why doesn't that work? I mean, that seems, of course, I should first just evolve for a time t, and then I should evolve for a time tau, and that should give me
the total evolution. What is going on physically, such that how do I conceptually understand that this does not equal the composition of these two things? First evolve T, say, and then evolve tau. Well, the problem is the following. We're only looking at a subsystem of the whole thing, right? So I have my quantum system, I have my quantum environment. I don't know why the system looks bigger than the environment, whatever. There's a time at which information can go between the system and the environment over, let's say, the first time interval. And then at a later time, t plus tau can come back. And if I'm only looking at a piece of it, I'm not accounting for the fact that information can come back. The structure of the map is such that the system is uncorrelated. From the environment at the input time. That's critical. I kept emphasizing that. You don't get a CP map if the thing that you put into it is not a product state. And after this first evolution, if we do this map over the first time evolution, the system and the environment become correlated. And so I can't just say at time t, there was, the joint system was this times an uncorrelated state. This state is the reduced density matrix of the whole thing. So it can't work out that way. And what's going on is the fact that information can flow back from the environment. Yeah?
So turning this on its head, can
Yeah.
you say that some measure of the difference between these two things is telling you something about how much information it has?
Yes, absolutely.
Okay.
Yeah. And so the degree to which that's not, that you could say maybe it's approximately true,
Yeah.
and the degree to which it's, not true, we can say it's still a positive map, but it's not completely positive. So what that is, this is related to in stochastic processes, what's known as a Markov versus non-Markovian processes. What's a stochastic process? A stochastic process is just a way of saying I have a probability of some random variable that depends on time. So I have, say, some probability of some random variable x that depends on time. And I might have some joint distribution where I say I have the probability of having value x sub k at time t sub k conditioned on the fact that it was k minus 1 at time tk minus 1, and it was k minus 2 at time tk minus 2, dot, 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 up to some x2 at time t2, x1 at time t1. So this is the conditional probability of the random variable being x sub k at this time for some time series. If it's Markovian, then what the whole history is irrelevant. It only depends what it was at the last time, and that tells me how to get the probability at a later time. If it's Markovian, then this conditional probability just depends on the last time. And that's the kind of dynamics we have when we think about, you know, flow in a differential form that we have for Hamiltonian evolution. But generally, stochastic processes, like in open quantum systems, are not Markovian. And what it means is, if I want to know how to evolve the state to some final time, I can't just look at it at some differential time earlier. I need, in principle, to think about what happened in the whole history from the initial time, because I have to think about how information can come back to my subsystem. If I treat the whole thing and don't look at a piece of it, then it's Markovian, always, because it's unitary. But if I look at a piece of it, then it's not going to generally be Markovian. Okay? Now, there are a subset of evolutions, and in some sense it's what Cole was alluding to, that we can approximate as Markovian. Okay? So what we're going to be interested in, because they're an excellent approximation, particularly in quantum optics, not so much in solid state systems, but definitely in atomic systems, is we want to think about a Markov evolution of the density operator. We've already seen it last semester. We kind of fudged it. We're going to fudge it a little bit more today, but we'll get under the hood more later. This leads us to what's called the Lindblad master equation. You remember that, Dan? Now, I never know, maybe when you spell these Russian names, is it FF or V? I've seen it both ways. Would you call it Markov or Markov? I don't know, but I put it this way.
Vodka could be vodka. Vodka could be vodka.
Yeah, I could speak Yiddish, but not Russian. All right. So this is our goal, and what we're going to do to get there is we want to look at a form of the evolution that is similar in spirit to this. Okay? So, what we want to look at is a CP map for evolution t to t plus dt that is Markovian. Okay, so what do we want that map to do? What that map should do is take the state at time t and evolve it. So we want a CP map that does that. And that CP map, if it's a CP map, every CP map is a Krauss map. Where the Krauss operators here are the Krauss operators that propagate me for a time dt. Again, I'm treating everything as time translation variant. these, in principle, these Krauss operators could depend on time, in the same way that the Hamiltonian could depend on time. But for the moment, I'm just not going to look at that case. And if this is something that does this, then we know what this should be is plus something that takes the initial state and is proportional to dt. It has to be of that form. When dt goes, it's only got to be first order in dt. When dt goes to 0, it does nothing. And there's something that it does to the initial state. Okay? This, cursive L is sometimes known as the Lindbladian map. Okay? And we can then say in a very, vapid, that doesn't have a lot of information in it, that we have a differential equation that if I just subtract this from the other side and divide by dt, I get the differential equation that says this. Okay? So the rate of change of the density operator is whatever this Lindbladian is acting on that. This is Markovian, right? Because it says that the way in which the state is changing at that time just depends on what the state is at that time, and not its whole history from 0 to t. Okay? Now, what we know is that if this is a CP map, then it must be a Krauss map. And if it's a Krauss map, well, and it has to have this form, then we know the form of the Krauss operators. Because this thing has to equal that. We could break this up into two kinds of Krauss maps. I'm going to break it up into a map, one that I'll call mu0. For reason, I'll just call it that. And then all the other ones I'll say mu greater than 0. So I sectioned off one particular Krauss operator from the rest. Why did I do that? What is special about this Krauss operator compared to all the rest? Well, I can always lump in, there is at least one Krauss operator that is near identity, meaning it is of the form, I'm going to let M0 be something near the identity, and that goes to 0 proportional to dt. I can always choose one of the Krauss operators to do that, because M0 dagger, M0 rho, M0 dagger will be of this form. If I drop, because dt squared is 0. Okay? So I can always choose one of them, but there's another choice I can make because of this conjugation. These guys aren't necessarily unitaries, they can be anything. And so I can choose the rest of the Krauss operators to be of a form that's not proportional to dt, but proportional to the square root of dt. We'll come back what the hell the square root of dt means, but whatever's left over is an operator we'll call L mu. So these are all the other Krauss operators that are in the Krauss map. That's the most general form of a Krauss map, which is something which propagates the state, maps the state to something that is first order in dt. Okay? These sets of operators, the sets of L mu's, are called the Lindblad jump operators for reasons that we'll talk about a little bit soon. the Krauss operators are proportional to the jump operators with the square root of dt in them, okay? Okay, so the L mu's can be anything. There's nothing that restricts the L mu's, but there's some relationship between this operator G and the L mu's. Because if we assume this moreover to be not only a CP map, but a CP TP map, and TP stands for trace preserving, not toilet paper. Then there's what we know is that the resolution of the identity is the sum of all the Krauss operators. This is the generalization of what we had for closed quantum systems that said U dagger U was the identity. And the fact that U dagger U was the identity told us that the near identity evolution was something that was a differential approximation to a unitary operator. But we don't have that anymore. What we got is this. So what does that tell us? Well, let's plug it in. M dagger M is equal to, or M0 dagger M0 is equal to the identity plus G dagger dt, right? That is M0 dagger M0. I dropped the G dagger G dt squared because that's 0, okay? dt squared is 0. And then we got sum over mu, L mu dagger, L mu dt. Okay, that's this term. So what does that tell us? Well, the identities cancel on both sides of the equation. And what I have is that G plus G dagger has to equal minus mu, L mu dagger, L mu. So what does that say about G, the operator G? Firstly, the right-hand side of this equation is a Hermitian operator. Okay, because L dagger L is Hermitian. This is Hermitian. So is this. G plus G dagger is Hermitian. But it doesn't tell us anything about the possibility of an imaginary part or an anti-Hermitian part. So what this tells me is that G is equal to minus a half sum over mu, L mu dagger L mu, plus some anti-Hermitian operator. An anti-Hermitian operator is one whose dagger is minus that. But it doesn't tell us what that anti-Hermitian operator is. It could be anything. And since it's anti-Hermitian, we can factor out an I, and because of the units, there's an H bar and an energy in there, you can think about the units. So think about that. And by definition, we call this minus I the Hamiltonian, or A is equal to that. We just factor out these units. With that said, we have the following. We have a Krauss operator, which is equal to something that I'm going to call H effective, where H effective is equal to H
minus I h bar over 2 sum over mu L mu dagger L mu.
Okay. So what I did is I defined G as minus I over h bar times what was left over. And what was left over is what I'm calling the effective Hamiltonian. The effective Hamiltonian has a Hermitian part and an imaginary or anti-Hermitian part. Okay? And that's one of the Krauss operators. The other rest of the Krauss operators are proportional to dt. The effective Hamiltonian Hermitian part H, the anti-Hermitian part is minus I over h bar sum over mu L mu dagger L mu. Okay. With that said, I need a new column. This is this one, this diagonal. So if we have the Krauss operators, now we have the map. It says that the time evolution gives me this. And we can plug them in. Let's do it. That tells me when I plug this in, I get, oh, this one's even worse. Let's see if the back is better. Yeah, maybe. See how long it lasts. So when I plug this in, I get the identity part, and then I get minus I over h bar, h effective rho, minus rho h effective dagger. Everyone see that? That's this part. And then I get plus sum over mu L dt. I'm an unhappy camper. I'll be happy now. Or if I subtract this off and I get a differential equation, I get this form of the Lindblad master equation, where the prime here says take the dagger. Notice there's a dagger over there. So this equation, which I can write out now, let's plug back in what H effective is. This is another form. We'll write it in terms of let's look at this very carefully because it's really important. This thing is something we've seen last semester. This is the Lindblad master equation. It's the equation of motion for the state for non-unitary evolution that we can consider to be Markovian. Notice the different pieces that we have associated with the master equation. We have the part that is the Hamiltonian evolution. And a part that I can think about as L rho associated with the open quantum system. Okay? So we see we have the part that would, just as we had over there, we have the Schrödinger equation, but we have an additional term, or a set of terms, that came from the fact that this was an open quantum system. Also importantly, there's a piece of this that we could have lumped together with the Hamiltonian and thought about it as an imaginary part of the Hamiltonian. You remember, I'm sure, from last semester that we talked about the fact that when we think about, things like dissipation, like in classical physics, we can think about putting in an imaginary part to the damping, to the frequency to imagine damping, an imaginary part, like an imaginary index of a fraction. And that part is part of the evolution, but there's another important part that's beyond that we wouldn't get a trace preserving map if we just had the imaginary part. We need this other term here. But the difference of them came from these different classes of Krauss operators. This is in the more formal description, and that's going to be important in our description of quantum trajectories in a few weeks. Very good. Maybe I'll pause for a moment for any questions. All right, let's take a look at this equation. We're going to want to, I just want to mention, I didn't derive anything from first principles here. There's no system environment interaction, no justification of the Markov approximation. I just said, let us suppose there existed a Markovian CP map. If there were a Markovian CP map, I can look at a differential evolution, how to take the state forward in a slight step in time. And if I assume that, it's beautiful. Math tells me it's got to be of this form. There's no other form that is possible other than the Lindblad form for a Markovian CP map. But once we have this, we've seen this before, let's just try to think about what does this evolution do, okay? So let's just consider the evolution due to the open system part. Okay? Forgetting about the Hamiltonian for the moment. We know how Hamiltonians evolve things. Let's just try to think about how do we interpret these Lindblad operators in the context of open quantum system dynamics. Okay? So I'll just write it down again because it's good to write it down. as many times as possible so that we can try to remember it. d rho dt is equal to L open on rho, which is minus a half the sum over mu anti-commutator. Let's write out the anti-commutator. Okay, and let's look at, let's say that I have some basis. I'll just label those states J. There's a basis of states of the system. Okay? And I want to ask, how does the probability to be in state J change as a function of time? I can call this the population, how much population there is in the Jth state. That is equal to that. Okay, so that's the diagonal matrix element of the density matrix. Tells me the population in that state. So that's equal to the following. It's minus a half the sum, or I'll write it this way, J sum over mu, L mu dagger, L mu rho, J plus J sum over mu rho, L mu dagger, L mu J plus J sum over mu, L mu rho, L mu dagger, J. Okay. So generally speaking, I now want to expand rho in this basis.
Why are there no Hamiltonian commutator terms there?
I'm just looking at the open system part of it.
Oh, just the open system. Okay, yeah.
Okay, I'm just asking that part. The Hamiltonian will do different things, but I'm just asking, what does this part do? Okay, very good. So now I want to expand rho in this basis, but it's typically the case, as we'll see, for just the open system part of the evolution, that the Lindblad jump operators don't couple the off-diagonal elements with the diagonal elements. They don't drive coherences. The Hamiltonian does. The Hamiltonian creates coherence given the initial population through Rabi oscillations and things like that. But typically, the Lindblad equations don't couple the diagonal elements, the populations to the coherences, or the coherences to the populations. They just couple them, diagonal elements couple diagonal elements, off-diagonal elements couple to other off-diagonal elements. So with that assumption, if I'm saying I'm only looking at how a diagonal element evolves, I'm just going to put in the diagonal part of this guy, right? So I'll just write this as the sum over k with a different dummy index of that. There are, of course, off-diagonal elements, but I'm going to assume they're not coupled, okay? So if I put that in, what I find then is the following equation. Because this guy, you know, J, what I'm going to get is the following. I get a rate equation.
I'm sorry, capital P is a probability?
Capital P is a probability.
Yeah.
It's the probability, so P sub j here is the probability to be in state J, sometimes known as the population. How much population is there in a particular energy level? So what I'm saying here is that the master equation gives me, for the populations, a set of rate equations that tells me how population changes in the different levels, where I've defined here this rate that takes population from the state K to the state J is being defined equal to the sum over mu J L mu JK squared, and gamma sub j is equal to the sum over mu J L mu dagger L mu J. You can see this term over here because when I plug this in, I'm only going to pick off the Dirac delta is going to pick off K equals J, and then get the matrix element here. I get a half plus a half is 1. So that's this term. Whereas in here, when I plug in the sum over some dummy index K, PK, I'm going to get the matrix element between of this guy squared. Everyone see that? So that's interesting. It gives us an interpretation of these Lindblad jump operators. What it says is that the matrix element, I can think about this also as a sum over mu where that's equal to this guy. So let's look at that and try to interpret what it means. What it say, okay, firstly, let's look at this equation. What it says is that there's a rate at which population leaves the state J. It leaves at the rate gamma sub J. And there's a refeeding of population from K to J at this rate. Okay, and that's just, rabbits and foxes competing and eating each other and whatever they do. So, yeah, I'm not seeing it. You can leave it to your imagination. But there's a competition going on, right? And populate rate changing, right? So, firstly, what is this rate? What it's saying is, firstly, it's a sum over all the mu's, which can represent different possible processes that take population from K to J. For every process mu, there is a rate. So this rate, oh gosh, which takes population from K to J through process mu, is the square of the matrix element of the Lindblad jump operator. So I should think about the Lindblad jump operator as something that's telling me about processes that can connect different states in some kind of jump. That's why the Lindblad operators are called jump operators, because they can think about them like a quantum jump that takes population from K to J. And the square of the matrix element is what that rate is, assuming there's some quantum process that's labeled by mu. We'll talk about what those mu's are in a moment, because right now they're completely abstract. There's no physics here at all. But this is really like Fermi's golden rule. It's a generalization of it. You know, Fermi's golden rule says something about transition rates, about the squares of the matrix elements, you know, between initial and final states. This is like that. Okay? What about this guy, this gamma sub j's? Well, if we look at the gamma sub j's, they're telling me the total rate at which stuff leaves J. And that total rate is given here. But if I shove in a complete set of states, basis states, always a favorite move in quantum mechanics, then what I see is that this is equal to the sum over all K, the rates at which I go from J to K. Because what's in here is the square of the matrix of both the K and the J reversed. So the rate at which that total rate I leave is all the ways I can get out of J and go to K. Okay. So that's interesting. That tells me that, you know, an interpretation of these Lindblad operators. The Lindblad operators tell me something about the rates at which I go between their matrix elements, tell me about the transition rates.
So this, thinking of a two-level system that's being pumped.
Yep. So that's an example, and let's do that example. That's the one that I'm about to do. Right now it's completely general.
Yeah.
We'll think about lots of different cases of this, but let's talk about the particular, let's talk about even a case that's not even pumped. It's just spontaneously emitting.
Okay. Then it's not open.
Sure it is. It's open because
Oh,
it's coupled to the vacuum.
To the vacuum, okay.
So, yeah, that's important. So let's think about our friend again, the two-level. There's an excited state and there's a ground state. And we know that population in the excited state will spontaneously emit, and population will decay at a rate gamma. We can, without any derivation, write down what we would say is the Lindblad master equation for this, because we know what the jump operator is. Why do we know that? We know that the rate of transition that takes me from the excited state to the ground state is gamma. I'm sorry, the other way around. Takes me from the excited state to the ground state. Okay? There's no thermal photons, there's no pumping, so the rate at which I go from the ground state to the excited state in the absence of anything else is 0. So with that, what are the jump operators? Well, there's only one jump operator, right? What we know is that the matrix element of the jump operator that takes me from the ground state to the excited state is 0. And its matrix element that takes me from is gamma. Right? So what's L? What operator can I write down whose matrix elements are this?
So lowering operator, some
So it's got to have a matrix element that takes E to G. So what should that be?
Raw E and then a cat G on the left.
Thank you.
And then a square root gamma.
And then a square root of gamma. That's it. So if that's the only jump operator, we can write down the master equation. Let's do it. Let's remind ourselves of that. So this tells me that the rho dt is going to be equal to, well, first of all, L dagger L is going to be gamma
The E and G should be swapped here, right?
Oh, sorry. Oh, I see. Yeah, I got this backwards. Yeah, sorry. Thank you. This is sigma minus. That makes more sense. Okay. So, let's say there's no Deriving. Let's put back in the Hamiltonian. The Hamiltonian is the Hamiltonian of the atom. We can take this to be 0. Just take the ground state energy to be 0. So H effective is what? Well, according to that, H effective is H minus I H bar over 2 L dagger L. Right? And that's what we have there. That tells me that this is equal to the energy minus I that's H effective. Does H effective have the form we expect to have? Indeed it does. It says, I can say that this excited state with this energy really has an imaginary part related to its line width or its spontaneous emission rate. Because the probability to be the excited state should decay at rate gamma. The amplitude decays at the rate gamma over 2. So this is my effective Hamiltonian. And the master equation then says that this is equal to minus I over H bar, H effective rho minus rho H effective dagger plus L rho L dagger. And this, if we plug that in, is that, which is equal to so what we see in this expression for the master equation is that the part that was the imaginary part of the Hamiltonian, the anti-Hermitian part, led to population decay. It took population decaying out of the excited state. Whereas this term is the refeeding term. It's the term that takes population back into the ground state after the spontaneous emission happened. And the rate at which that happens depends on, well, was it in the excited state, right? So we can get, for example, the population rate equations, which says that it's pretty trivial in this case. Tells me how population, which handwriting going, should I fix that? Okay. So that the total population is conserved, right? The sum of the total amount in the excited and the ground has to be conserved, trace preserved. Moreover, we can ask about coherences. How do the coherences change? So if I ask, how does the off-diagonal matrix element evolve as a function of time? What do I get in that case? Well, firstly, this doesn't contribute. There's no feeding of coherences in this problem. We'll come back to the point of feeding of coherences. So if there's any change of coherence, it's coming from this term. Now, since this guy is diagonal, it's not going to change. We'd have to have a Rabi term to change the coherence. So the only thing that's coming from is from the Lindblad term over here, and you do a little work and you find that is this. Okay. This is the term that we would call T2, right? It's the way in which coherences decay. In this case, it's coming only from population decay because it's not a dephasing channel. It's an amplitude damping channel. Now, I want to emphasize, interestingly, you remember perhaps when we were discussing this last semester, if we didn't have this term, this thing kind of looks like an effective Schrodinger equation. It's a Schrodinger equation that wouldn't preserve the norm of the wave function or the trace of the density operator because it's not trace preserving. But we could just write it if we wanted to, and to the degree to which this term was negligible, that's a good way to actually solve an open quantum system. Just put an imaginary part in the Hamiltonian, that's kind of good enough. But this term is different. It doesn't look like a Schrodinger equation. And we're going to see that that's very important in terms of our conceptualization of what's going on in the math equation, in that we can think about it a part of the evolution that's kind of like non-unitary, deterministic Schrodinger evolution, and then something that's not. Something that's related to the fact that there's a quantum jump. There's a stochastic process by which population started here and ended there. There are quantum jumps. And those quantum jumps are here. There's one last thing in the last minute I want to say. What the heck was this mu about? There's no mu here, but we can imagine, as we will see, a more complicated decay process. Maybe we didn't have a two-level atom. Maybe we have an atom with different sublevels. say we have a case where we have J equals 1 in both cases. This is the ground state manifold and this is the excited state manifold, but they have magnetic sublevels with -1, 0, +1 as the ends of J's. And I might have a -1, 0, and +1 here. And maybe I start here, I could decay like this, or maybe I can decay like that. Because there are selection rules which tell me how I can decay. And this would correspond to the emission of a photon whose angular momentum was 0 along the quantization axis. It's parallel to the quantization axis, and so it's called pi. Whereas this polarization is perpendicular, and it's called a sigma. In this case, it would be a sigma minus photon that was emitted. So these correspond to different channels. The total decay rate will depend on, so I might, those mu's might represent different, say, polarization states of the photon that's emitted. So we'll see examples of that in master equation, where we'll have multiple jump operators corresponding to something about the environment that we might measure.
So decay rate would be measured, or can you derive that from basic principles?
Yes, we will derive it from basic principles in the same way that we derive the so-called Einstein A coefficient, which is the rate of spontaneous emission. It's, of course, as we will see, an approximation, because we can never get these things. It's a super good, approximation doesn't mean bad. Approximation could mean awesome approximation. But we can never get from the Schrödinger equation something which is irreversible. The irreversibility is coming through some approximation. And it's through that approximation, and the Markov approximation in particular, which we'll talk about again next time. And we did, for those who were in the class last semester, when we did the Wigner-Weisskopf, it's the same calculation yet again. We'll do it again on Thursday. Yes, we all do. I do too, every year. Yeah.
The refeeding part of that equation seems just as continuous and deterministic as the Hamiltonian part, so it's not clear to me why you think that should be called like stochastic jumps more so than the Hamiltonian part of the evolution.
Well, it's true. Okay, it's a little bit. What I'm saying is there's no equation motion I can have for a single member of an ensemble. If I were to think about the state as a statistical mixture, then this refeeding term involves a stochastic process that has both jumps or no jumps. That gives me something that is what will change the mixedness.
So is it that you can't write that term in terms of what's happening to a pure state?
That's right.
Okay, I see.
That's what's right. Whereas this is equivalently, I can write this equation is equivalent to this.
I see. So it's the pure states are.
It's the pure states stay pure. Now they don't stay normalized, but they're just pure. Whereas there's no way to write that as an evolution of a pure state. And in that sense, it's stochastic. Very good. All right, we will continue this discussion on Thursday.